Paul asks, why are some physical constants dimensionless? Okay, we're now going to dive into a completely different area of human or scientific endeavor. So let's talk about units. Let's talk about dimensions. You say something is 2 feet long, 2 meters long. Something lasts 2 seconds. Something has a speed of 3 meters per second. There's a number there, a 3, but then there's a unit that tells you sort of how you should be, how to interpret that number. Why are there physical units? Why is it the case that it is a different kind of thing to talk about a length than a time? I think in the end, it kind of relates to the way that we as humans perceive things. How to say this? I think that when we are talking about length, for example, we are imagining, comparing the length of a thing. Like I remember, I think in Magna Carta, it says 1 inch is the length of the king's thumb or something. I'm not sure if that survived very long in British law, but it was that way in 1200 or something like that. But in other words, there's a length, and we can compare sort of this physical extension to something about us and our bodies and so on. And similarly, when there's a time, there's a certain experience that we have for that period of time. And these are distinct things, length and time, for example. Now, it gets, this is a little complicated, actually. One of the questions is, what are the fundamental dimensions that are relevant to things? Like, for example, length is a dimension, but volume is not a separate dimension. Volume is derived from length. A volume is like the cube of a length. You've got, width, depth, height type thing. And those 3 together determine volume. And so volume is not an independent dimension from length. It's like length cubed. And so the question arises, well, what are the independent dimensions of kind of the physical world? And what's usually been identified, mass, length, time, these are uncontroversial ones. Then it gets a little bit more controversial. Then there's amount of substance, the number of atoms measured in moles. Another one, there's luminous intensity measured in candela, in the NKS units, in the SI unit system, the standard metric unit system. And that's essentially the number of photons that exist in some case. And then, what am I forgetting? There's, well, some people think that angle is a separate kind of unit of measure from length and so on. And oh yeah, another one people sometimes talk about is bits of information, that's a sort of independent unit of independent, non-convertible dimensional thing about the world. But all the other kinds of things like, acceleration is length time to the -2, or, force or energy is mass length squared divided by time squared. And that many things that you might think energy is a very different kind of thing from length and time and so on, but actually there's a way of representing energy in terms of mass, length, time, and so on. Okay, so it really depends on what you think is sort of fundamental in the world, how many really independent things there are. So for example, the speed of light converts length and time. So the speed of light says, in 1 nanosecond, in 1 billionth of a second, light travels about a foot. So in a sense, once you have the speed of light as kind of a constant, as a thing that is out there, then time and length become, in a sense, immediately interconvertible. And in a sense, you don't really need a separate notion of dimensions of length and dimensions of time once you say, oh, there's the speed of light as well. And there are, in standard physics, there are several quantities that are kind of these converters. So speed of light converts length and time. There's also the gravitational constant, the thing that determines the strength of gravity, that converts, let's see, that's a more complicated set of units, but that essentially converts mass. And yeah, in the end, because it determines the curvature of space, it relates mass and length. The gravitational constants relates mass and length. And a third thing is Planck's constant, the kind of fundamental constant determining the way quantum mechanics works, and that relates energy. Well, it has units of energy times time, but it gives you relations between essentially things like energy and time. So, in a sense, once you kind of these constants like the speed of light and so on, you can, if you as a human say, my unit of length is a meter, that's what I relate to as a human. My unit of time is a second, that's what I relate to as a human, then the speed of light is a thing you measure about the world. But there's a sense in which the speed of light is just a way of defining those units. It's not really a thing you measure about the world. It just says, given that you've got a certain elementary time length, time unit, for example, the speed of light is just the conversion factor that goes from that to the elementary length unit. So it's an interesting question in our model of physics, where these dimensional quantities really come from. And because in the end, in our model of physics, everything that exists in the universe is just some whole collection of elements in these hypergraphs that are being rewritten, et cetera, et cetera, et cetera, that everything is ultimately just a piece of computational data. And so how could there ever be some sort of meaningful physical dimension of a thing? I think in our models, there really is, at some level, we have to say, well, there are these updates that are happening to this network that represents the universe. How quickly are those updates happening? Well, we could say the updates happen when they happen. And we are observers embedded within that system, and we're getting updated too. And there's nothing to say about how quickly the updates happen. We can also say, if we look from outside the system and we imagine that there's an absolute clock ticking, we can say, how quickly do those updates happen relative to our sort of absolute clock that we've set up? And then we can start talking about an elementary time, maybe it's 10 to the minus 100 seconds or something, that is this sort of elementary clock ticking time for the universe. This is a complicated area, actually, of understanding the where dimensionality comes from, where this notion of things you can measure, because, you know, in our models, something like mass is just a counting of the number of things that are happening in this network. Length is just a counting of the number of edges in this network. Time is just a counting of the number of updates that happen in this network. So how can it be the case that there is a sense of there being sort of a unit, a thing that isn't just a number, that is our sort of representation of a length or something? I think maybe the way to think about it is this, that within the system, there are, we are embedded within the system, we're made up of these same sort of atoms of space and so on. And one question is, how many atoms of space are there in a typical human? Maybe the answer is 10 to the 100, let's say. So, and somehow that number is what somehow turns itself into what we're doing effectively by talking about meters and seconds and so on, is we're factoring out having to actually know that number. We're just saying in a human is about a meter tall. We could say a human is 10 to the 100, elementary lengths tall, but we don't know that number. So we're sort of factoring that out, and we're inventing this kind of symbolic unit of a meter and saying we're about a meter tall. And so we never have to discuss, we never have to know what the actual number of elementary lengths that we are is. Now, in traditional physics, there are certain combinations of quantities with units and so on, which are dimensionless in the sense that they are just numbers. Just like I'm describing in some sense in our models of physics, everything is just numbers. There are things where we already know they're just numbers. A pretty famous one is a thing called the fine structure constant. But in general, the fine structure constant measures essentially the strength of electromagnetism. Pretty much every theory that involves the interaction of particles that has the property of being, that it has certain nice mathematical properties, it's a renormalizable theory in quantum field theory, all of those theories have dimensionless so-called coupling constants. A coupling constant measures essentially the strength of interaction between particles. So you'd say, if you've got two particles and they're colliding, and you ask, what's the probability that they actually scatter each other as opposed to just zoom past, like particles, you know, ships passing in the night, particles just not having an effect on each other. What's the chance that they actually have an effect on each other rather than not? That's proportional to the coupling constant, so-called coupling constant. And for different theories, whether it's quantum chromodynamics or quantum electrodynamics or something else, there'll be different values of those coupling constants. But those things in certain kinds of nice mathematical theories tend to be dimensionless things. And so that's an example. And they're just saying, what's the probability of this interaction happening? So those are examples of where you get sort of dimensionless quantities that arise in standard physics. Curiously, the gravitational one is not dimensionless, and that produces all kinds of complicated tentacles about the theory. But it's an interesting question. Actually, there's probably more to figure out about sort of the way that dimensional quantities arise. But I think my basic answer there that really dimensions are introduced in a theory like ours, where everything is ultimately computational and ultimately just counting, that dimensions are a way of sort of bulk sort of representing, you know, the size of a human is, and then it's a thing like a meter, rather than saying it's the number 10 to the 100 and so on. By the way, in our theory, there really is just one sort of truly dimensional thing you have to nail down. It's either the elementary length, the elementary time, a thing we call the maximum entanglement speed, which is the analog of the speed of light in branch shield space for quantum mechanics. But these are, any one of those things would sort of nail down all the other parameters and determine them. Let's see. I might just comment just for interest about the whole idea of dimensions. Let's talk about it a little bit. Let me just clarify one thing, by the way. Oh gosh, I forgot. I'm so embarrassed. I forgot two important fundamental dimensions that exist. Charge and temperature are two other ones. But you see, they're all a bit flaky, because what is charge? Charge is basically a count of the number of electrons, the number of electric charges you have. Just like luminous intensity is a count of the number of photons you have. And just like amount of substance is a count of the number of atoms or molecules you have. Those are just counts of things. In a sense, they seem like very fake units, because they're really just counting things. And they're not something which has some different existence, not just accounting. Now, temperature, again, another complicated one, because temperature is one where temperature is the average kinetic energy, the average energy of each sort of degree of possible motion of an atom or something. It's not really an independent thing. It's really something which, once you know the structure of a system, you kind of know that, you know, the energy per unit volume of the system divided by the number of degrees of freedom and so on is essentially the temperature. So even though in kind of the usual way of setting up unit systems for the last, I don't know, 50, 70, 100 years, people have said temperature, that's a fundamental unit. that's it starts to look a little bit flaky when you start realizing, well, what's this thing made of underneath? It doesn't look as independent as you might think. Now, units are a very complicated area. In Wolfram Alpha, we have kind of and Wolfram language, we have kind of the world's, by far, I would say, best, most organized way of handling units and best sort of curated collection of units. There are about 10,000 kinds of units that people discuss about different kinds of things. And there are units that are, the perceived amount of sound measured in fons, for example, or, well, my all-time favorite unit is moles per acre, which is a unit of soil aeration, where moles is a chemical unit of amount of substance, but in this particular case, it doesn't mean that. It means the number of little critters who are, digging up the soil and aerating it, the number of those per unit area measured in acres. There are about 10,000 of these different kinds of units. They all ultimately can be written in terms of 5 or 6 or so of these mass length time, but ultimately even those can be written, as soon as you have a theory of physics, those get to be written in terms of even less, and ultimately in terms of almost nothing. Now, units are really complicated. Like, for example, just a few days ago, we were talking about temperature units, and one of the things that's an issue is if you have temperatures, you always talk about degrees centigrade, degrees Fahrenheit. Why are you talking about that? Well, it's because it is not an absolute, those are not absolute temperatures. Those are what you're talking about. Okay, so temperature is essentially the temperature measures the average energy per degree of freedom. So when you have the temperature of a gas, for example, is determined by the average energy that all those gas molecules are whizzing around, knowing that they can be going in the X direction, the Y direction, the Z direction, and so on, knowing that they can be spinning around, things like this. The formula is a half kT, where K is Boltzmann's constant, T is the temperature. That's the average energy per degree of freedom. You move in this direction, you spin around, you do this or that. But when people measure temperature, they usually are measuring the difference in temperature between the difference between sort of the energy the gas has when it's got this much heat in it and the energy the gas has when it has this much heat in it. Now, there is the notion of absolute zero minus 273.16 degrees centigrade. That's the point at which essentially all of that motion pretty much stops. That's the point at which you've kind of, there's no, and that's an absolute temperature. But a lot of what's actually measured and what people discuss are temperature differences. And confusingly, there haven't been really good notations for the temperatures versus temperature differences. And so we just introduced, actually will be coming in a Wolfram Alpha and a Wolfram language very soon, a little notation with a delta for representing difference in temperatures, because a difference in temperatures is a kind of quantity that you handle in a different way from an absolute temperature, so to speak. There are computations you can do with temperature differences different from the computations you can do with an absolute temperature. To mention dimensional analysis is this somewhat mysterious area of kind of, I don't know what, physics or something. If you're trying to work out, okay, a famous example is this. Let's say you've got a model airplane and you've got a real airplane. And the question is, the model airplane is, you want to know, in order to get the same kind of pattern of airflow over the model airplane and over a great big real airplane, what should the ratio of the speeds of those things be? Is there a speed for the model airplane and for the real airplane such that the pattern of airflow over those two things will be the same, even though there are very different scales? And so it turns out you can work that out using dimensional analysis. That means there are only certain quantities that can matter. The speed of the airplane can matter. The density of the air can matter. The viscosity, the flowiness of the air can matter. The size of the plane can matter. So it turns out that if you take those quantities, and those are the only ones that matter, then you can package those up only basically in one way into a dimensionless object, a thing called the Reynolds number. And so what you then realize is you can scale the viscosity of the air, the speed, the length, and so on. You can scale those in different ways. If you preserve this Reynolds number quantity, then you'll get the same overall pattern of flow. And so there are a few nice examples where this works out well, where you have this idea that by pure dimensional analysis, by just knowing what quantities are important and seeing what mathematical combination of those is dimensionless, that tells you how those quantities have to scale in order to get sort of the same physical results. Those are there are a modest number of examples where that works. It's a little bit of a strange thing because basically you have to know what quantities are important in determining how a system behaves. And what's a bit surprising is as soon as you say, oh, and there's an extra quantity that might be important, it kind of blows up the possibility of doing this kind of numerical, dimensional analysis. It's a case where the more you know, the less you can figure out, so to speak. And when you have just, oh, it's only these four quantities that matter, you can conclude things about dimensional analysis. Probably the most famous in the wild, I think this is a real story. I've been told it by several people, including at least one or two who were there, that when the first atomic bomb test explosion was done in 1945, there was a physicist called G.I. Taylor who was there, who was trying to figure out just how strong was this explosion, how big was the explosion, and you could figure that out. There were certain quantities about the size of the fireball and the this and that thing, and so famously, G.I. Taylor used dimensional analysis, sort of in real time, so to speak, to try and figure out how many kilotons was the explosion, so to speak, and that's a famous example of dimensional analysis. I have to say, it was also involved in, at that time, people were concerned that if you detonate a nuclear explosion in the Earth's atmosphere, that you might ignite the atmosphere, that you might basically start a process where the atmosphere just starts burning everything, so to speak. And it was an analysis a bit like that dimensional analysis, which led the physicists who were working on this to conclude that no, it won't ignite the atmosphere, probably, to detonate a nuclear explosion. I'm not sure in today's world, well, I don't know, some very silly things happen in today's world, but I don't know whether people would again have the nerve to actually detonate a nuclear explosion, given that at the time it really wasn't, I think, completely clear. There were pretty good arguments that it wouldn't ignite the atmosphere, but it certainly wasn't known for sure, because after all, people don't imagine that there's ever been a nuclear explosion in the Earth's atmosphere before the ones produced by humans starting in the 1940s. Well, let's see. That's a nice story from Thy Lord here. Speaking of strange units, they say there was an operating system that required time to be specified in micro-fortnights because although its value in seconds is close to 1, it forced the administrator to think about what they were doing when setting the system time. That's rather nice. Let's see. Oh yeah, I should just explain one confusion of language here. When I'm talking about dimensions, yeah, this is a collision of different things. There's dimensions as in X, Y, Z, height, going up, sideways, left, right, up, down, in, out type thing. That's a notion. Well, let's see. That's the 3 dimensions of space where we're talking about dimensions in which we are kind of saying, these things are related concepts, but they're not the same. There's kind of the the ways in which we can move around and the different ways in which we can move around, this other notion of dimension that I've been yakking about for a while here is a notion that is about units of measure and kinds of dimension, as in we are, I don't know how to say this. This is a very confusing thing, actually. It's like we've got the mass of something, and that is a dimension of the thing as its mass, but it's not dimension in the same sense as we're talking about 3 dimensions of space. Someone's commenting here, dimensionality versus units. Yes, that's right. I mean, it's the dimensionality of space, but unfortunately the word dimension gets used, and it's not a completely different use, because it is that space has 3 dimensions, like 3 length dimensions, so to speak, and 1 time. Space-time has 1 time dimension, but the notion is a little bit different from these way of doing units. All right, I think I have to go to something different here, although there are lots of very interesting questions that have come in here. William asks a question: does empty space have an entropy? As a matter of fact, I've been thinking about that very question, because I've been thinking about the foundations of the second law of thermodynamics. And the answer to that is yes, it does have an entropy. And there are particular cases in which that's very measurable when there are black holes, but I think you can think of it having an entropy at all times. And I think there's a very interesting relationship between that and the way gravitational fields work. And maybe we'll talk about that another time.